Okay. Likewise, if we have stress xi, it's so over here for stress xi, I have this distance over here, and we call this y2. From here to here is our y2, and from here to here is also our y2. So this is also equal to mz over izz y2. And you find stress x at point J is also equal to mz over izz multiplied by y2. So therefore, stress x I is also equal to stress x j. So this condition satisfies what? Symmetry loading, right? We call it symmetry loading because of the stress field. Okay, so symmetrical loading, I'm going to write down symmetrical loading is based on, in fact, two things. Okay, it's in fact based on two things. One is based on stress field distribution. Two, bending moment is only applied in one axis. So for this case is mz, right? So the moment over here for all three of them, they are all only in what? Mz. If you have two moments acting on it, that is unsymmetry. That we'll do next week. Okay, when you have two moments, right? I and j should be negative. Y should be negative for point I and j. Yeah, I just took it out, okay? I just took it out. Okay, you're right, Michael, you're right. So the theory, you have a lot to absorb now, right? You have a lot to absorb over the past, what? 1 hour, 5 minutes, okay? This is the foundation of bending, okay? That is all we are going to learn. Then we're going to apply to different situations. I repeat again, that's all you need to know. Okay, then like shearing stress, right? I wrote down a set of rules. We apply the rules to anything and everything after that. Okay. So the first one, what is the first thing to remember? Okay. So let me quickly recap. When we were over here, the most important thing to take note is the what? The moment vector. The head of the moment vector is always in what? Compression. The tail end is always in what? Tension. Okay, this is the most important thing we learn. Then the second thing that we learn over here is if the structure is under symmetrical centric loading, right? The neutral axis and the centroid are in the same position. Okay, so i.e., this is the centroid, right? The one in green is the centroid. The one I shade in red is the neutral axis. They all are exactly on the what? Same position. Then the third thing that we learn, they have shown to you that you'll understand, symmetrical loading has nothing to do with the load distribution. Right? Has nothing to do with how the force is applied or the load is distributed. More important is the stress field. The condition where stress alpha is equal to stress beta, or stress I is equal to stress J. For all the trees cross section, you meet the condition, right? And the most important thing, whether is it symmetrical loading or not, is the moment can only be applied in one axis. Repeat again, the moment can only apply in what? One axis. Okay, these are the rules. You have to embrace the rules. Okay, if you don't embrace the rules, then there's problem in remembering the what? Fundamental. Okay, you have to know the rules. Right. So the next thing I want to address, okay, before we do example, is failure analysis. Okay. We did a bit of failure, not a bit, we did a lot of failure analysis in shearing stress. Bending moment also have some failure analysis that we have to learn. Okay. So the next thing that I'm going to address is AI stress IO. Okay. So the next one I like to address is the similar characteristic between
Sir, you are muted.
Can you hear me now?
Yeah,
How long was I muted?
like 10 seconds.
Thank you for letting me know. So at point A is a pin, and at point B is a roller. Okay. So now, why failure occur at point C? Right. So how can we address it? Why failure occur at point C? Okay. So I'm initially going to show the simply supported beam. Okay, I'm going to show the simply supported beam. So if we draw our free body diagram, X, Y, and this is rotation about Z. So we know over here you have AY, and over here you have BY, and over here you have P, and we know that AY is P over 2, BY is also P over 2. Okay, and the distance of the entire length over here is equal to L. Okay, so we are going to form, okay, now I'm going to teach this more in detail later, maybe in week 10. Okay, but I'm going to introduce you to how to get the shear force and bending moment equation first. Okay, so we are going to determine shear force and bending moment equation. So you all know what to do with the shear force now, yes or no? Right, you know what to do now. Okay, now we are going into the what? Bending moment. Okay, bending moment diagram, because we need the bending moment vector now. Okay, so here we go. So we are going to form the limit between point A to point C. So this is where our point C is, right? So our limits are 0, x to L over 2. Okay. So we're going to draw the diagram. This is point A. This is our x. And at point A, we have a load over here, right? Which is equal to P over 2. Okay. And then we're going to assume that the shear force over here is coming down is V as a function of x, and the moment as the function of x over here. Now, why this direction? Okay, now because our analysis is carried out from left to right. Okay, it's going in this direction. This is what I mean by, because it's depending on how your x is moving. So we are starting from left hand side, going to right hand side. So on the right hand side, the shear force is always coming down. The bending moment is always going in an anti-clockwise. So over here is what we assume positive shear and positive bending moment. Okay, left to right analysis. Okay. Then from here, we do static analysis. We're going to carry out static analysis. Okay. Positive is going up. Summation about forces in the y direction is equal to 0. Okay. So it's P over 2 minus by V as a function of x is equal to 0. V as a function of x is equal to P over 2. And this is true from 0, x to L over 2. Okay. Next, we are going to take moment now. Okay. We are going to take moment at the dot that I'm going to draw. Okay, the dot that I draw is where we're going to take our moment. Why? Because the moment is dependent on the x magnitude. I repeat again, the moment is dependent on the x magnitude. Okay, so over here, moment. So I mentioned about moment in the z direction, anywhere upon x value is equal to 0, right? So P over 2 will do an anti-clockwise direction. So P over 2x or Px over 2 plus by m as a function of x is equal to 0. So m as a function of x is equal to px over 2.